Question 5 from Paper 2 of the 2024 Higher Physics Examination of the SQA. A group of students are participating in a demonstration that models the redshift of light from a distant star relative to an observer. The star is initially stationary relative to the observer. The students leave the star at intervals of 3.5 seconds and walk towards the observer. Each student represents a wavefront of the light emitted by the star. And for 3 marks in part A, it says determine the wavelength of the light represented by the students, and the students representing the wavefronts walk with a constant speed of 1.5 meters per second. Okay, we have got a wave equation. If we can remember that, V equals F times lambda. And to find the wavelength, we just have to rearrange to get wavelength lambda equals V divided by the frequency. Now, we do know that the frequency is going to equal to 1 divided by the period t. And the period t is the time taken for one complete cycle to pass. And that's going to be 3.5 seconds when you think of the period, because every 3.5 seconds one person is going to pass. So the period of that wave is going to be 3.5 seconds. And we already know the speed, so all we have to do is change our wavelength equation. Lambda equals V divided by F. So we've got V divided by 1 upon t, because that's what the frequency is. That's going to be equal to V times capital T. And t is going to be the period, which is 3.5 seconds. So the wavelength here is going to be equal to the speed, which is going to be 1.5 meters per second, multiplied by the period, that's the time for each person to go past, is going to be 3.5 seconds. And if we do that in a calculator, we end up with a wavelength of 5.25 meters. And we can do that to 2 significant figures. It's going to be 5.3 meters to 2 significant figures. Question 5b. The demonstration is repeated and the star now moves at a constant speed relative to the observer. The wavefronts are still emitted from the star at intervals of 3.5 seconds, and you get the pattern now observed is shown below. Now, for 2 marks, we have to state if the star is moving towards or away from the observer. And the first thing we look at is how the observer measures the waves approach them, or the wavelength approach them. And you can see that each successive wavelength is going to become bigger. So the observer is going to see each successive wavelength becoming bigger. In other words, it's going to be stretched out. So that's our first clue. Each successive wavelength is getting longer. What does this imply? It implies the following. It implies that there's a decrease in the frequency. Now, when you get a decrease in frequency, you think of the Doppler effect. What does that tell us? Well, the Doppler phenomena tells us that a decrease in frequency is a result of the source moving away from the observer. So in this case here, what we have got is the source is moving away from the observer, because the observer is seeing the wavelength being stretched, in other words, redshifted into the longer wavelength. And that's the justification for your answer. The wavelengths have been stretched out, therefore the source of the waves is moving away from the observer. Now, if you're not convinced with that, take a look at this excellent little simulation here, and you can see we have got a galaxy here, and the galaxy, as we can see, is sitting there still. But if I move it away from the Earth, you can see that definitely the wavelengths have been stretched. So any source of waves which moves away from the observer, the wavelengths will be stretched longer. And that's the answer to that particular question. Question 5, continued part C. Redshift is evidence for the concept of the expanding universe. Another piece of evidence for the expansion of the universe is Olber's paradox. And for 2 marks, we're asked to explain how Olber's paradox, also referred to as the dark sky paradox, supports the concept of the expanding universe. Well, first of all, let's see what the Olber's paradox really is. And to do that, we have to look at an observer looking at the night sky and the darkness of the night sky. Now, in those days, Olber's theory on quite all the astronomical theories at that time was that the universe was basically infinite, which meant it went on forever. It was static, which means it was not moving, and it was eternal, which means it was always there and always will be there. Now, if we have that model of the universe, then no matter where we look into the night sky, then we should be looking along the lines of many stars. Every star on that line should have its brightness, and all those brightnesses should be adding up to give us one big brightness, because basically you're looking through an infinite universe with infinite number of stars, then all the brightnesses of all the stars you should see should make the night sky completely ablaze with light. That's why it's called the dark sky paradox, because we don't see that. We see a dark sky. Now, because of the concept of the redshift, that gave you evidence that the universe was expanding, and along came Hubble. We've got a new understanding of the universe, and that universe, we can think of it as an expanding universe. And the stars that are really far away from us, well, they're going to have a receding velocity which is going to be very big. How do we know that? Because Hubble came up with his famous equation that the receding velocity v is equal to Hubble's constant times the distance they are away from us. So these stars at the edge of our universe, if there can be an edge to the universe, are travelling so fast, their recessional velocity is so fast, that their wavelengths are going to be stretched out so that we can't see it. Their wavelengths, which from these stars, are stretched out into the red end of the spectrum so much that they're redshifted, and the wavelength is in the infrared, and of course we can't see infrared light. So that's a reason, because we can't see the light, it appears dark. So there you have how Albert's theory actually supports the expanding universe, because if the universe was expanding, we should be able to see millions of stars in our line of sight, and those stars should be adding up the brightness to give us a blazing sky, but they don't. But that's because we believe there was an infinite, static, eternal universe. Hubble and the rest of the people come along to discover that the universe is actually expanding, and the stars far out in the universe that are moving away from us are going to have a big recessional velocity because their distance is so great. And that big recessional velocity stretches out the wavelength of light they emitted into the infrared region, and therefore we cannot see them, and therefore it's dark. And that's why we see a sky dark at night, because quite simply we can't see those other stars. Question 5c part 2. State one other piece of evidence that supports the concept of the expanding universe, and that is the cosmic background radiation. That was a famous discovery made when a special infrared telescope was pointed up to the sky, mapped the full sky. Because if we have just said in the previous question that all those stars and galaxies, their wavelengths have been shifted into the red end of the spectrum, the redshift, the infrared part of the spectrum, because of the recessional velocity, then we should be able to detect that infrared radiation, and that's what we did. So that was a further evidence that supported the concept of the expanding universe, that the cosmic background radiation existed, and the temperature of this radiation was in fact 3K, which was the temperature predicted all these years, 13 billion years after the initial expansion of the universe. That was the temperature that was predicted if we had the model of the expanding universe, 3K. So that was confirmed with the cosmic background radiation and the temperature of 3K.